In the recent years, a lot was promised with regards to the autonomous cars. Recently, Waymo's self-driving car has crossed the 10 million miles milestone, but it still struggles with some basic scenarios such as left turns, merging with traffic, driving through crowded areas. And other industry leaders had some unfortunate accidents that raised a lot of questions. We are moving forward in steady steps, but it looks we are not quite there yet. So let's take a look at some of the technological challenges that we still need to overcome on the way to full autonomy. When we think about car perception system, we first of all think about object recognition, being able to recognize perfectly all the agents on the road. But is it enough? If we look at this picture, can you clearly understand what's going on here? So this is more or less how the car sees things. In order to get to human-level perception, we need much more than that. We need to be able to contextually understand the situation. We need to understand the basic rules of the game. We need to understand trajectories and behaviors of all the agents on the road. And eventually, we need to be able to predict what's going to happen next. And most state-of-the-art artificial intelligence, deep learning systems are very far from those capabilities. Ability to drive in any conditions, if it's a night or other weather conditions, it's not trivial for humans. But the lack of ability to contextualize and predict makes it even harder for the deep learning systems because it's difficult for them to complete the missing pixels. A good example of such difficulty is the Uber accident that happened in Tempe, Arizona, killing Elaine Herzberg, who was crossing the road with her bike during the night hours. Even more, we don't really know the system capabilities in such conditions because most of the testing is done in nice weather conditions such as California and Arizona.
There's another Uber accident.
Imagine a baby is born, and now the parent has to present a huge, clean, labeled, structured, representative training set for them to be able to learn. Sounds very tedious and even impossible, right? Yet, this is exactly how the most advanced artificial intelligence deep learning systems learn today. They are highly supervised. They require a clean, huge, representative training set to be able to learn. And the quality of the results is, in many cases, is very correlative to the quality of the results of the training set you provided. For example, if you miss in your training set for pedestrian people wearing coats and holding umbrellas, the machine will not be able to identify that type of pedestrian on the road. And the size of the set is huge. For example, Waymo's pedestrian identification solution required millions of manually tagged images, and most of us probably participated in gathering it without even knowing about it. Deep learning works as a black box. Sensor input goes into the huge multi-layer network, some magic happens, and we get the output. In most of the cases, the result makes sense. But what if something unexpected happens? What if there is a stop sign and instead of stopping, the car starts speeding up? As things stand today, it's really, really hard to understand why. These are some famous examples how slight modification of a picture, where the human eye doesn't even pay attention, confuses totally the system. So this inability to debug, to analyze, to understand, raises a very big problem of trust with the manufacturers and eventually the public. And last but not least is the power consumptions of those systems. The next wave of transportation will be electric cars. The manufacturers and the policymakers have all agreed on the effort of pollution reduction. But if you open the trunk of a self-driving car, you will see a miniature power plant there. And what is interesting there, that more than 40% of the power is consumed by computers running the AI algorithms. With such power consumption, moving to mass production is unrealistic. So, it is true, deep learning and state-of-the-art algorithms have some great achievements. But is it enough to bring the required breakthrough to overcome these challenges? Incremental improvement will not be enough. We need a new, more advanced AI system that will be able to learn on its own without training sets, is capable of human-level perception, works in any conditions, transparent and explainable, and all of it working with low power consumption. I would like to introduce Cortica's autonomous AI that addresses these challenges. Despite a heavy investment in machine learning algorithms, brain perception is still much more powerful. Cortica's autonomous AI leverages the power of the brain and mimics the way it processes information and learns. We started our journey at the Technion in 2003 while trying to reverse engineer the brain. We've connected to a real rat brain and tried to understand how it learns. We generated a model, a computational model of the cortical networks, and observed the way the mammals and humans learn. Through that, we generated a generic, fully self-learning system. It is based on 15 years of R&D, protected by more than 200 patents and inventions. Cortica's autonomous AI enables human-level perception. Similarly to humans, Cortica's autonomous AI does not require any training set. It uses a raw feed from the camera and generates robust and lightweight representations, Cortica signatures. And then it uses those signatures to automatically cluster similar objects, situations, behaviors without any human intervention. One car with a camera generates 30 megabytes of data every second. It is 2.5 terabytes of data every day. And if you don't need to label and tag that data, you can instantly leverage all that data to learn. This is a huge learning opportunity. And this is just one car, just one day. Cortica's robust signature gets to human-level perception in multitude of weather conditions and lighting conditions. In the unfortunate Uber accident, we ran the video that was released by the press agencies, and we were able to identify the bike rider 0.9 seconds before the hit. This could have saved her life. One of the most advanced cognitive functions in people is our ability to predict. We predict unconsciously all the time, especially when we are on the road. We try to understand what each of the agents on the road is going to do. Cortica's ability to understand situations allows us to use unlabeled big data of raw footage, and by understanding the situations, we can learn, and finding similar situations in the past, we learn the behaviors. And then we can use that knowledge to predict what is going to happen. So, for example, Cortica's system knows that the bus that is loading passengers is not going to move forward until it is done. Or it can predict that if there is a significant obstacle on the road, the car ahead of us is going to change lane to bypass it. And another example, if there is a person who is crossing the road using their phone, we know that there is a higher chance that they are going to cross on a red light because they're not paying attention. Our flat architecture is hardware agnostic and low compute. We use a generic signature, the same signature for any function. Object recognition, lane detection, behavioral understanding, prediction, all use the same signature. This reduces a lot the power consumption of the system. Through our collaboration with Renesas, a Japanese chip giant, we have a production-ready system that is 10 times lower compute than any existing solution on the market, and 10 times lower than any most optimized CNN system in the academia. Cortica system consumes only 0.5 watts. And the last thing, the transparency. Cortica's signature and concept structures are fully transparent and allow the developer to trace what exactly happened, how the certain results was achieved. We use an additive approach to update our concepts, meaning if you want to change the concept, we do not need to retrain the whole thing. We just add or remove a specific signature ID that contributed to a particular result. This makes the testing much easier because there can't be a situation where we fix one thing while breaking 10 other things. Another interesting thing is this additive approach allows us to update the concepts in real time on the edge, which allows a new type of vehicle-to-vehicle communication. Oops. So to summarize, we believe that Cortica delivers the breakthrough required to get to the next level of autonomy. Thank you.